Sensation and perception is absolutely one of my favorite topics for this class. I didn't think I would like it when I was going to take a class in it, but it turned out to be absolutely one of the most fascinating aspects of psychology for me. So when we start looking at this topic, we need to first separate sensation and perception. Now, in the everyday sort of way of looking at things, in layman's terms, sensation and perception are used more or less interchangeably. Within a scientific context, within a psychological context, we can't do that. Sensation we define as the process of receiving raw sensory information and sending it to the brain. Sensation occurs outside of your brain. Sensation occurs only within the peripheral nervous system. Once that information reaches your brain, it's all about perception, which is the process of selecting, organizing, and making sense of that sensory information. It's important to note that the brain itself has no sensory nerves of any kind. You actually can cut into a conscious living brain, and they do for brain surgery. They require that the person be conscious. That you can cut into a conscious living brain and the person will not feel anything. The brain itself is incapable of sensing the world around it. It requires sensory input from the peripheral nervous system. And so everything that you are aware of in the world around you is all perception. None of it is real in the way that you think of it as being real. Okay? Color, for instance, doesn't exist outside your brain. It's just wavelengths of light. Your brain makes color real. Your perception of those wavelengths makes color a thing. All right. When we begin the process of sense and perception, we begin with sensation, and sensation begins with sensory transduction. That's what happens when some kind of environmental stimulus, whether that's light or sound or chemicals or pressure or temperature, these pieces of sensory information are transformed into the electrochemical signals that can be used by your neurons. That transformation is called transduction. Your sensory receptor cells exist for all of your senses, in your eyes, your ears, nose, tongue, skin, almost all over your body really you have these sensory receptor cells. And they're all specialized to take in exactly that one type of sensory information that no other kind of cell can take in. When those cells are exposed to that sensory information, they send a signal to the neurons that are attached to them, and then those neurons transmit those impulses to the brain to be processed. That's all transduction is, and that's the limit of sensory information. That's the limit of the process of sensation. But because it's so specialized, we almost have to look at each of the sensory nerves individually to see how they work. All of your sensory nerves have two different kinds of threshold. That is simply the limits of their ability to process information. Each of your senses has what we refer to as an absolute threshold. An absolute threshold is the smallest amount of stimulus that a normal, healthy sense nerve can detect. 50% of the time, you have a 50-50 chance of successfully detecting that sensory information. The dimmest light you can see, for instance, if you had a hallway that is perfectly straight and perfectly dark, you could detect the flame of a single candle from 30 miles away. That is, for instance, from the campus of Angelina, you could detect a candle flame in Nacogdoches. Okay? Given a perfectly straight, not curved around the surface of the earth, but a perfectly straight, perfectly dark hallway, you could do that. In absolute silence, you can detect the ticking of a watch from as far as 30 meters away. One drop of perfume can be detected in 300 cubic meters. of space. 1 teaspoon of sugar can be detected in a gallon of water. So you can see that these absolute thresholds are actually extremely, extremely small and delicate and careful. Your senses are extremely powerful. It's simply that most of the time we exist in a flood of sensory information that prevents us from picking up these incredibly fine, minute details. The difference threshold is actually significantly different than the absolute threshold. Rather than having a bare minimum amount of information that you can take in and detect a change in your sensory information, difference thresholds function on something of a ratio. We can refer to this as a just noticeable difference in sensory information. And it's very much a ratio. To put this in example, if you were in an absolutely dark room and someone lit a match, you would notice a dramatic change in the amount of light in that room. You would be able to detect much more information about the room through your eyes because of the small amount of light produced by the match. However, in a brightly lit classroom, perhaps during the day with all the lights on, if someone lit a match, chances are your eyes wouldn't even notice unless you were actually looking at the match, because the difference, the change in the amount of light in the room is so minute that it's not enough to trigger a change in how you perceive the amount of light in the room. With some training, you can actually reduce your difference threshold. For instance, a trained musician can detect an alteration in pitch. They can detect when something is out of tune much more accurately than someone who is not a trained musician. When we're constantly exposed to the same sensory input over a long period of time, our ability to process that information is reduced. Okay? And simply, we refer to this as sensory adaptation. And what it is simply is that your brain has stopped perceiving that sensory information. It stopped selecting it for attention. It's not necessary, it's not important. This unchanging piece of information is no longer relevant unless it does actually change. For instance, you put on your clothes at the beginning of the day and you notice, maybe the weight of the shirt or how tight your pants are. But over the course of the day, you stop paying attention to that and it sort of slides out of your consciousness until maybe after you eat a big meal and you have to adjust yourself. Things like hearing the air conditioner, hearing the train outside your window, which is what I'm hearing now. This sort of fades out over a period of time unless it becomes something relevant to you. Some forms of sensory adaptation become a little bit more specific. Things like hearing a baby cry is not something you really ever adjust to. We actually have a biological drive that makes us respond to babies crying, particularly your own baby, because you can identify your own. Whereas a thunderstorm will put me to sleep, and even though the thunderstorm might be a little bit louder than the crying baby, there's no way to sleep through a crying baby. Okay. Um, People who put on perfume and they end up sort of bathing in it because they can't smell it anymore, but everyone else can. Again, it's sensory adaptation, and they become used to the smell of their perfume, so they think it's faded, when in fact it hasn't, and they end up choking people to death on their own perfume. As we begin looking into the individual senses, we're going to start with the chemical senses. That is, the senses that detect chemicals in the world around us. Olfaction detects chemicals in the air, and gustation, which is the sense of taste, detects chemicals dissolved usually in saliva, although certainly in other fluids as well. When we smell things, okay, chemical odorants, usually esters, are carried through the air, and we inhale them through our nose, and they reach the nasal mucosa. Okay? The nasal mucosa is a small patch of sensory nerves uh, approximately between your eyebrows. Okay, it's fairly actually high up in your sinuses. It's a relatively small patch, about an inch square, so about the size of a postage stamp. This has about 5 million olfactory receptor cells. Okay? And these receptor cells bind to specific esters in the air and send impulses to your brain to detect the kind of smell that you're receiving. We can detect about 10,000 unique smells. Although most people haven't trained their sense of olfaction to be able to differentiate all those different smells. People who have and can differentiate all those different smells actually get paid really, really well by, for instance, wine companies, perfume companies, um, even food production companies who need to make sure that their product is consistent across all of their batches. These individuals are paid extremely well to ensure quality control in that way. This is a visual here of the different sensory information. You can see down here, this is actually the nasal mucosa. This is what's exposed to the outside world. And as you get up here, this is into the olfactory nerves and into the brain through that way. So most of this image is actually part of the tissue of your brain, and those little dots down at the bottom, those are your odorant molecules that become attached to the sensory receptor cells. Gustation is the other chemical sense, and usually detects these chemicals that are dissolved in saliva or occasionally in other fluids. These chemicals fall between the bumps of your tongue. These are called the papillae. You were probably taught that these were your taste buds, but that's actually not the case. Each papillae holds about 200 taste buds, and they're actually tiny cell-sized pits on each of those bumps. The bumps increase the amount of surface area on your tongue so that you can have more taste buds. Your taste buds are your sensory receptor cells for taste, and they, of course, detect these chemicals. Now, we don't have nearly as many taste buds as we do olfactory receptor cells. And in fact, we can detect far less from our sense of taste than we can from our sense of smell. This is an image of a taste bud that is sitting on top of a papillae. You can see that the food falls, or the food chemicals fall into the taste pore and are detected by the taste receptor cells. When we perceive taste stimuli, when these food particles fall into the taste pores, we actually have 6 types of taste receptors. Now, the first 4 we've known about for a long time: sweet, sour, bitter, and salty. And you were probably taught that you can taste sweet on the tip of your tongue and bitter on the back of your tongue, and sour and salty are somewhere in the middle. This is not the case. You actually have taste buds for all of the different tastes, all over your tongue, the roof of your mouth, and down into your throat. But we also have 2 more types of taste receptors that we weren't aware of until fairly recently. Umami is a very subtle flavor. It's a savory flavor. You can taste umami in unseasoned beef, in milk, in rice. This flavor is so subtle that we actually don't have an English term for umami, which is why we use this Japanese term. The other taste that we just discovered a year or 2 ago is actually carbohydrates. Carbohydrates have a flavor, and we didn't think that they did, but we now recognize that we can in fact taste carbohydrates, which makes sense because they're such an important part of our diet that we need to be able to detect them and taste them and even enjoy that flavor. Spicy is not a flavor. You don't have any taste buds for spicy. In fact, most spicy flavors are caused by a chemical called capsaicin. The capsaicin causes a mild chemical burn that you perceive as flavor. Okay, that's why your eyes will burn if you're cutting a jalapeno and touch your eye. It's the same reaction, except that it happens around your taste buds, so you perceive it as a flavor. Humans are one of the only animals that will willingly eat capsaicin, which is why it exists. Flavor is generally the result of taste and smell working together. Because we only have those 6 types of taste receptors, if your nose is plugged up, it's very difficult to taste anything at all. That's why no food tastes good when you have a head cold. Because your sense of taste is reliant on your sense of smell, and being able to determine those 10,000 different odors helps you differentiate and define one flavor from another so that you can actually determine what it is that you're tasting. The tactile senses, and it is actually fairly important that we put a plural on that. The tactile senses is actually a combination of 4 distinct skin senses that we can actually separate and look at the different nerve cells that detect these 4 different senses. Pressure, warmth, cold, and pain all exist as tactile senses. So far, we have only found the sensory receptors for pressure, and those only in the places where those sense nerves are the most common. That is, the fingers, the lips, the bottoms of the feet, the hairless portions of your skin. We know that there are a variety of different kinds of cells. Free nerve endings, these are the ones that we've sort of detected. They're near the, Meissner's corpuscles are the ones that we've detected. Okay? And they detect sensitive touch, and there's a lot of them. Free nerve endings should exist near the surface of the skin, detecting a variety of different senses. Merkel's discs should detect light to moderate pressure and exist at a slightly deeper level. Ruffini's end organs should detect heavy pressure in the movement of joints. This is actually how you can tell where your body is in space, by using Ruffini's end organs. And then the Pacinian corpuscles should respond to vibrations and heavy pressure. But again, we haven't detected any of these. We can't find them. They have to exist, because there has to be something that's transmitting this information, but we can't locate them. One of the really interesting things about the sense of touch, and the sense of pain in particular, is that some things that you wouldn't think are pain actually are. Things like tickling, all right, is actually a pain response. And we laugh at it because that is a biological reaction to say, I'm okay, everything's all right. But laughter is a pain response. When you perceive touch, and in particular when you receive pain, because pain is an excellent example of this, the sensory neurons register some kind of information, and that information is relayed to the thalamus and then to the somatosensory cortex. Pain responds a little bit differently, because pain actually has 2 parallel pathways that run together. The first of these pathways is the fast pathway, and you would think the fast pathway would hurry up to get to your brain, but actually it doesn't. If you consider that if you touch a hot pot, you jerk your hand back very suddenly, even before you register that you're in pain. The reason for this is actually your fast pathway. That pathway is heavily myelinated so that the signal is transduced very quickly, but it doesn't get all the way to your brain. Instead, this fast pathway gets only as far as your spinal cord, where it triggers a reflexive response to pull your hand back. This response bounces from your hand to your spinal cord and back to your hand to pull back. At the same time, the slow pathway, which is much less myelinated, sends a signal to the brain to register, you're in pain. The reason for this is the brain is way too slow. The brain has to process an enormous amount of information, so by the time it gets around to saying, oh look, you're in pain, you should do something about that, the damage is already done. Whereas your spinal cord can trigger that instant reflex to yank your hand back and have done with. So these 2 parallel pathways absolutely work in unison to protect you from damage in a lot of ways. Slow pathway pain tends to be a lot softer. It takes, yes, fast pathway pain. All right, we'll start with the fast pathway. Fast pathway pain deals with quick pain. You get stabbed by a needle. You have this heavily myelinated pathway that gives you this sharp localized pain and allows a fast response. If you're stabbed or something like that, your fast pathway takes over. And for the slow pathway, these unmyelinated axons, this is your nagging, burning pain. Slow pathway pain is sunburn, is tickling, is itching. All these things are slow pathway pain, and so we communicate using slow pathway pain some long-term damage that has been done. We know that there are individual pain thresholds. We know also that men have a higher tolerance for fast pathway pain, whereas women have a higher tolerance for slow pathway pain, which is evolutionarily helpful, but it's also not significant. Just like with most of our differences between men and women, the difference is actually so small that individual differences are far larger. The gate control theory of pain actually explains, for instance, why scratching and itch works. Itching is a pain response, and scratching is also a pain response, but they're two different kinds of pain response. Because itching itself is a slow pathway pain response, it creates this nagging, burning pain. When you scratch the itch, you generate a fast pathway pain response, which essentially closes the gate on that slow pathway response, so you only respond to that fast pathway pain. The gate remains closed for a while, which is why the itch goes away for a period of time, and then returns later on when the gate opens again. So this is our gate control theory, that more intense or more urgent forms of pain actually block different pain, right? It blocks that slow pathway pain when you're receiving fast pathway. We also have brain chemicals called endorphins. Endorphins are essentially natural opioids, and they block pain. They are painkillers inside your brain. People can actually use these. Intense physical activity or sex can actually produce endorphins to help reduce the amount of pain that you're feeling. Consuming large amounts of chocolate will do the same thing, actually. The auditory sense, hearing, is detected through sense nerves in the ear. Sound has a set of properties that exist in order to process information. Now, when we draw a sound wave, it tends to look like this. However, that's not really what a sound wave is. If you were to describe this point, it would be a point where the molecules of air are pushed together, and this point is a place where the molecules of air are pulled apart. So sound isn't a wave of highs and lows, but a wave of high and low pressure. Okay? And that's important to consider. When we look at the properties of sound, we can look at frequency, which is the number of cycles per second. Okay, and we define that as hertz. This is a wavelength, and we can measure the wavelength, but we usually do that more with light than with sound. With sound, instead, we measure frequency, because most sound travels at approximately the same rate, particularly through air. We can determine how many cycles per second, how many of these peaks per second cross a certain point, and that's the frequency. That determines the pitch of a sound. The more of these peaks that pass, the higher pitch the sound is, and the fewer of them, the lower pitch the sound is. Okay. We can also look at amplitude, which is the height, from the highest peak to the lowest trough. The bigger that amplitude is, the louder the sound is. So the higher you turn up the volume, the bigger the amplitude becomes. And this describes how much pressure you're putting on the air around you. Another of the qualities that sound has is called timbre. Timbre. Timbre describes the quality of the sound. Timbre is how you can tell a violin from a trumpet, how you can tell your mom's voice from your best friend's voice, just by hearing it. Timbre is the quality of the sound, because most sound isn't a nice smooth curve like this, but actually has a variety. There's a carrier wavelength with a whole bunch of other wavelengths grouped around it. The process of hearing is actually a fairly complex one. Sound waves are channeled into the ear through the pinna, that is the exterior portion of the ear that you think of when you talk about someone's ear. The pinna acts as a channel to pass these sound waves into the ear canal, the hole, down into your ear. It's about half an inch long, or about 1 inch long rather. And the sound waves pass through this channel and strike the tympanic membrane, that is the eardrum. Tympanic literally describes drum-like, and then membrane, it's essentially a flap of skin. This causes the tympanic membrane to vibrate slightly against the three smallest bones in your body, the hammer, the anvil, and the stirrup. These three bones serve to actually amplify the tiny vibrations in the air, so that when these vibrations pass into your middle ear, they're actually far more powerful. Now this hammer, anvil, and stirrup vibrate this area right here, the cochlea, this spiraled snail-like structure inside your ear. The stirrup hits the oval window, which is part of the cochlea, and causes the fluid inside the cochlea to vibrate and move. It moves back and forth. And as it does, it triggers these delicate hair cells inside the cochlea to vibrate and move along with it. These cells, when triggered, send information to your brain about vibrations in the air. These hair cells are extremely vulnerable and one of the few parts of your body that will not regenerate once damaged. The hair cells will never grow back. We're not sure why, and we absolutely have been working on ways to regrow the hair cells. But in all honesty, we don't even know necessarily how they work. The hair cells might all fire at whatever frequency happens to be occurring, or the hair cells might fire, each cell might fire only at a specific frequency. We don't know, because we can't take a functioning ear apart and figure it out, although we're learning more and more and more as we experiment, for instance, with cochlear implants that allow people to hear more and more information. The visual sense is perception of a tiny piece of the electromagnetic spectrum called visible light. The visible light spectrum is actually extremely small. If you lined up the electromagnetic spectrum with, for instance, alternating current circuits in Los Angeles Harbor and cosmic rays in Boston Harbor, you would find the visible light spectrum in a relatively small area in Missouri. It's actually quite tiny, and the wavelengths are extremely, extremely small. We measure the wavelengths of light in angstroms, which is a unit of measurement that we have no other use for, really, except to measure the wavelength of light. But these wavelengths are picked up and transduced by optic nerves inside your eye. We begin this process as light enters the cornea. Now the cornea is a thick protective layer on the outside of your eye. If you put a contact lens in your eye, you are placing that lens against your cornea. Okay, this is really the only part of your eye that you could touch without damaging your eye. Don't touch your cornea without a reason, please. From there, this clear cornea allows most of the light to pass through it. And then it passes through the pupil. If you look at your eye and see the small black dot in the center of your eye, it's actually not a black dot. It's a hole that allows light to pass through it. The reason it appears black is that the inside of your eye is extremely dark and not particularly reflective. So very little light leaves the eye and it appears black. Around the pupil, the iris is the colored portion of your eye, and it's actually a muscle that helps open and close the pupil so that you get the right amount of light passing into your eye. The lens sits just inside the pupil, and it is exactly what you would think it is. It is a lens to help focus the light, and because it's fluid, it can expand and contract in order to accurately focus the light at different distances to match what you need to be looking at. This light is projected across the aqueous humor to fall upon the retina. The retina is the tissue at the back of your eyeball that contains all of your photoreceptor cells. There's two specific spots on the retina that are of particular interest. The first of these is the fovea. If you're looking at something directly, looking specifically at it, particularly if you're reading, what you're looking at will be focused on your fovea. This is the point of your eye in which you have the most cones. And we'll talk exactly about what a cone is here in a moment. But the fovea has the most cones, and as a result, you get the clearest, most detailed image at that point. Near the fovea, the blind spot is the part where the optic nerve actually attaches to the retina. And at this point, there can be no cones and no rods right there because it is essentially a hole in the back of your eye. It's important to have this, otherwise the information couldn't be transmitted to your eye. But it's also important that your blind spots are in two different locations. So very rarely will you actually be able to see where your blind spot is. Instead, it's necessary for you to cover up one of your eyes in order to find your blind spot. And there are actually ways that you can find your blind spot. You can look them up on the internet. When the light falls on the retina, it can hit either rods or cones. Now, almost all animals that have eyes have rods. Rods were the earlier version of visual sensory apparatus. These were the first to evolve. Rods detect light and darkness, and that's pretty much all that they're good for. They detect black and white vision and grays, okay? But they are very good at also detecting motion. You see your rods mostly on the periphery of your vision, that is on the edges of your vision, as well as when all the lights are off and all you can really see is black and white. And you see motion very well. And this is important. If you have, the grass rustling out on the corner of your eye, you want to be able to quickly turn and focus on it. And you want to be able to find that motion very quickly. So rods allow you to do this. Rods are much heavier in prey animals, things like sheep, horses, cows, that sort of thing. Prey animals have a lot of rods. And actually, you have a lot of rods, about 120 million rods. You have more rods than you have cones by a long, long way. But rods aren't as accurate. Rods produce a very fuzzy, indistinct image. Cones developed much later, and cones give us good, clear central vision, good color vision, but they require a lot more light. Cones cannot operate in low light, and as a result, when it's dark, we don't see color very well at all. The fovea at the center of your retina is almost all cones, and we only have about 8 million cones in our eyes. So, but it's enough. It's enough to let us see the colors of things. It's enough to give us really clear central vision so that we can accurately see exactly what it is that we're looking at. Neural impulses are transduced by the rods and cones and sent up your optic nerve into the occipital lobe of your brain where it can be processed into vision. We've had a couple of different theories of color perception. The older version of color perception is referred to as the trichromatic theory, and there are actually some holdovers of this trichromatic theory still in your life. If you look into your color printer, for instance, you can see that you have 4 different inks. You have black, but you also have what appear to be red, yellow, and blue. It's not actually red, yellow, and blue. It's magenta, cyan, and yellow. We believe that these 3 colors were the primary colors that people could see. And we believe that we saw those 3 colors, that we had those 3 kinds of cones. And from those colors, we can make a wide variety of colors, and the trichromatic theory works okay. There are a couple of things, however, that the trichromatic theory cannot explain. And as a result, we had to come up with a different theory of color perception in order to explain things like, for instance, color after images, which I'll talk about here shortly. The opponent process theory was developed to explain certain things like color after images. And what it is that the activation of a particular cone inhibits another cone, that these cones act in concert with one another so that you get sort of different frequencies. What we suggest is that these opposing cells exist in red-green, yellow-blue, and black-white pairs. And with these 3 pairs, we actually are able to detect all of the colors that we can. The opponent process theory suggests that if you're not perceiving anything, if you're just looking, for instance, at a white surface, then your eyes will, then any given of these cells will transmit perhaps that wavelength. Okay? Then if you start looking at something red, you start giving off this much tighter wavelength, and you'll forgive my drawing with a mouse. And then if you look at a green, then you produce this much slower wavelength, and your brain reads that and interprets it as color. This allows us to have after images, and what actually appears to be occurring is that if you look at, for instance, something that's green for a while, your brain begins to interpret that green space as though it were white. So when you look at the white space again, you perceive for a moment that it looks red because your brain is interpreting that that wavelength has sped up some. So it must be red because it's sped up. So that's essentially how this opponent process theory works. And we're going to look at an example of opponent process so that you can see it happen. This is what we're going to look at. And if you look at the little white dot in the very center of this image for about 30 seconds, and I've got a timer here, so I'm going to let you stare at that. Try not to blink, try not to look away. We're going to give about 30 seconds for you to let this relatively familiar image sink in, but you'll notice that the 3 images are off, right? You have green instead of red, black instead of white, and yellow instead of blue. This represents those 3 opponent process pairs that are going to exist. Now, if you've stared at this white dot for this period of time, when I move to the next slide, you should see this image in a much more familiar color. You see that flash of red, white, and blue instead of yellow, green, and black? That is your color after image, and this opponent process theory explains that, whereas the trichromatic theory cannot. This is another example of an after image illusion. If you stare at the little square in the center, you should begin to see a green dot that is circling, and eventually those purple dots may actually fade out completely and be removed from your vision. This is an example of an after image illusion, which is also part of sensory adaptation, where you stop processing the purple image because it's not necessary anymore. Now, when you were in grade school, you were probably taught that you had five senses: vision, smell, taste, touch, and hearing. You actually have more than that, because we have what we refer to as the vestibular and the kinesthetic senses. These senses provide information about the position of your body parts and the position of your body. The vestibular sense relies on uh, these the Ruffini's end organs to know where your joints are so that you can determine where your body is in space. The vestibular sense allows you to eat a sandwich without getting peanut butter on your forehead. And it is something that you have to learn, but it's an important skill, and we all sort of start picking up this vestibular sense very quickly. The kinesthetic sense detects motion in your body's orientation in space, and it is actually controlled by the semicircular canals that are attached to the cochlea in your inner ear. These sense the rotation of your head in three dimensions by using a different set of hair cells. And it's the same process, for instance, if you have a coffee cup and you rotate the coffee cup, suddenly the coffee doesn't begin to move just because you've turned the coffee cup. This is what happens inside the semicircular canals of your head. However, if you keep turning the coffee cup, eventually the coffee is going to start swirling inside. And then if you stop turning the cup, the fluid continues to swirl. This is what causes dizziness. That's why if you reverse direction after spinning for a while, you can actually stop being dizzy, sort of. The vestibular sense is controlled here. These are your semicircular canals, and they exist in three dimensions in space so that no matter how your head moves, the semicircular canals can detect it. It's actually really important that these are in your head. Injury to any other part of your body can be healed relatively quickly, but injury to your head is a disaster as a point of evolutionary survival. So we detect the motion of our head because the rest of our body will pretty much follow what the head does. And that's why these semicircular canals are in your head rather than in your torso. So those are our primary senses. And when we start looking at senses, when we stop looking at senses, we can start looking at perception and how we process sensory information. Often when we process sensory information, it's necessary to organize that information. And there's two basic ways to organize and process this sensory information. We can use bottom-up or top-down processing. When we use bottom-up processing, it tends to be when we're looking at something that's brand new, something that we've never seen before. And we take in all the details of that object in order to construct a larger image of what it is that we're looking at. I imagine bottom-up processing as, this is my mnemonic for it. If you stand at the bottom of a forest, all you can see is a whole bunch of trees. And we process all of these trees sort of individually and put them together to get an image of what the forest will look like. With top-down processing, if you're flying above the forest, you can see the forest itself, and you just sort of have to know that there's all this other information, all these trees that make up the forest. So with top-down processing, you're using previously learned information to recognize and interpret the information coming into your brain. Top-down processing is easier. It requires a lot less energy, and so we sort of do top-down processing automatically. If you look at, for instance, a highlight magazine where you have all the hidden picture images, where you have to find, oh look, there's a pizza instead of a flag here, right? What they're forcing you to do is use bottom-up processing to examine the details of that image rather than taking the image as a whole, because at first it looks just fine because you're using top-down processing to process that information rather than the bottom-up processing to find what's wrong with the image. Where's Waldo is another great example of these hidden picture puzzles where you have to do this bottom-up processing in order to find the image that you're looking for. The master-apprentice effect is an excellent example of bottom-up versus top-down processing, where a master of a craft will tend to use top-down processing and may miss what's wrong with the object that they're trying to fix. Whereas the apprentice will look at each individual part and may actually be able to find and solve the problem before the master can, because they're looking at the object from a bottom-up process. When we perceive the world, we have to organize it. And we tend to organize our world in what we refer to as a Gestalt fashion. We use these Gestalt principles in order to organize the world into a whole piece rather than into individual details. We have a lot of these Gestalt principles, and we looked at these very early on, but one of the big Gestalt principles, and these are sort of the big ones that are really obvious to see. You can look at the top piece. This is a figure ground image where you can look at it and you can see either two people looking at each other or a decorative vase. But it's very hard to see both at the same time. You can flip back and forth between them, but seeing both at the same time is virtually impossible, because whatever you're looking at becomes the figure, and anything you're not looking at becomes the background. And that's essentially the figure ground effect. Proximity effects suggest that we group things together because they're close together. Okay? You can see in the first one we have 3 big hearts and 3 little hearts, and then we have 2 big, 2 little, 2 big, and then we have 1 big, 4 little, 1 big. We group them together because they're close to each other, but we also group them together because they're similar to each other, which requires you to jump down to the bottom to look at this similarity, right? Where you can see that there's an S or a 5, depending on how you look at it, depicted in these green dots, again, because they're similar, but also because they're in proximity to one another. We also have continuity and closure effects with this, because they're individual dots. It's not really a 5, it's not really an S, it's a set of individual dots. But we use closure and proximity effects to make, and continuity effects to make that design into a single perceptual unit that we can use to organize that information. Gestalt principles never work individually. They always work in concert with one another. And it's important. Without these Gestalt principles in effect, without us organizing our world in accordance with these rules, we could not watch TV. We could not organize our perception to see, oh, that's my friend, right? You would instead have to go, oh, that looks like my friend's eyes, and that looks like my friend's nose, and that looks like my friend's hair, and maybe it's my friend because they have all of these very similar features. We can instead organize them into a single perceptual whole, even many times when we can't see the entire image. This is another great example of figure ground effects. If you start looking at this image, this is what we refer to as an ambiguous image. You can either see an old woman or a young woman, depending on how you look at it. And if you start with this being the chin right here, then you can see a young woman, her eye is here. Okay, this is her eye and her nose, and she's sort of facing away from you. I'm going to delete those so that we can see the young woman a little bit better. But if this again is her chin, or rather if this is her nose here and then her mouth is here, then you can start to see the old woman present in this image, where she's wearing a shawl and looking more in profile rather than looking away from you. This is a very common example of figure ground and ambiguous images. We also have, as I said, proximity and similarity rules. We group nearby figures together and we group similar figures together. Right? And then closure is a tendency to perceive incomplete figures as whole and complete. We fill in the gaps, essentially. When we start trying to figure out how far away something is, there are actually two different kinds of depth cues that we can use. The first kind is monocular cues. Monocular literally means one eye. These are depth cues that you can use if you only have one eye, or if you're like many prey animals and you have your eyes on opposite sides of your head. This allows the prey animals to have a much larger field of vision, but it becomes much more difficult for them to tell exactly how far away something is. On the other hand, it's not super important that a horse know how far away the mountain lion is. It's far more important that the horse know that there is a mountain lion, right? That makes sense. But to a certain extent, we can start to tell how far away things are by using these monocular cues. We can use, for instance, interposition. When one object blocks your view of another object, you can see that the blocked object is further away. For instance, if you're looking at a teacher at the front of your classroom, and you can't see that teacher's legs because their desk is in the way. Even if you only had one eye, you could then determine that the desk is closer to you than the teacher is because the desk blocks your view of the teacher. We can also look at elevation, that is the height of objects inside your visual field. The further away something is, the higher it appears inside your visual field. And this is actually because your visual field is a cone that extends out. And an object that's here very close appears much lower in your visual field than an object that's here quite far away that appears much higher in your visual field. Even though they're at the same level, those two objects, one of them appears much higher than the other simply because it has further to go to reach the bottom of your visual field. We can also look at texture gradients. We see a lot more detail when objects are very close. So if it looks like, for instance, just a field of green, it must be further away than when you can see individual blades of grass. Linear perspective exists if you stand on train tracks, for instance, and look down the tracks, you can see that they appear to come together at what artists refer to as a vanishing point. This is actually linear perspective, and it simply describes that these parallel lines appear to converge in the distance. So the further away it is, the closer things appear to be. And again, this is because we have a cone-shaped visual field. Shading exists largely because our atmosphere is oxygenated. In our atmosphere, things that are far away appear to have a blue or purple coloration to them. This is because oxygen is blue. Usually there's not enough oxygen to emit a blue image, except if you look up into the sky, you can actually see oxygen glowing with a blue light. And if you look, for instance, at mountains far in the distance, they look purple. We know those mountains are not purple, right? Most of the time they're actually covered in trees, so they're green. But because they're so far away, and there's so much oxygen between your eyes and those mountains, they appear to be purple because oxygen has colored those mountains. And you sort of get used to it, and you learn that things that have this coloration are a little bit further away. Okay. We also memorize familiar size and relative size of objects. If you look out and you see a fully grown oak tree that's about 2 inches tall, you know that that oak tree must be fairly far away because oak trees are not 2 inches tall, right? That's part of why bonsais can actually mess with your perception a little bit, because they look like fully grown trees. They are fully grown trees, but they're only like a foot tall. And then relative size is simply that close objects appear larger than far away ones. So if the mountain lion appears to be taller than the tree, you know that the mountain lion is significantly closer than the tree, and you should probably do something about it. Right? The other form of depth cue that we have are binocular cues, and there's actually fewer of these. Binocular cues require that you have two eyes in front of your head. We have two eyes in front of our head. Mountain lions have two eyes in front of their head. This is a hunter configuration. Hunters do in fact still need to know that prey is there, but hunters need to know exactly how far away that prey is. It's important that hunters be able to determine if they're close enough to pounce. And so these binocular depth cues give you far more information about exactly how far away something is within a particular range. It's important to note that binocular depth cues only work out to about 100 meters. So they're actually relatively short range, whereas monocular depth cues happen at essentially an infinite range. Okay? That's why it's hard to tell whether whether the moon is closer than the clouds, except when the clouds move in front of the moon, because binocular depth cues don't work at that range. There's two binocular depth cues. The first is convergence. The closer something is together, your eyes actually cross in an attempt to focus both eyes on that object. And the more your eyes cross, the muscles in your eyes read how much tension is on them, and your brain interprets that as determining how close the object is. There's also retinal disparity. If you close just one eye and then close the other eye instead, you can see that objects shift in your field of vision back and forth just a little bit. And this is referred to as retinal disparity. The closer an object is to you, the more retinal disparity there is. 3D movies use retinal disparity in order to give you the illusion that objects are coming closer. By casting two simultaneous frames, the closer the object is, the more disparity there is between those frames. And because the glasses filter out half of that image from each of your eyes, each eye is only receiving one of those partial frames, causing your eyes to perceive that image as getting much closer. This is why some people get headaches or even nauseous in 3D movies, because you're relying on retinal disparity and ignoring convergence, and their eyes continue to attempt convergence, and it causes the movie to go out of focus, and it causes their problems, right? It causes them to have physical difficulties similar to car sickness. We also perceive the world as being a constant, right? We perceive objects being the same size no matter how far away they are. We recognize, for instance, that a house is not 6 inches tall. Even when it appears to be 6 inches tall, it looks like we could hold it in our hand. We know that it's actually very far away. This is a Gestalt thing that we refer to as size constancy. Shape constancy allows you to see that an object is the same shape no matter what angle it's viewed from. If you open a door, for instance, it appears to change shape from a rectangle to a trapezoid. It's not a trapezoid. It will never be a trapezoid. Your brain interprets that it's not a trapezoid, even though in the actually two-dimensional space of light falling onto your retina, it appears to be a trapezoid. You interpret it as a three-dimensional rotation. That's shape constancy. We also have color constancy, being aware, for instance, that a tennis ball remains green even when we see it in the dark and it looks gray. This is a fun optical illusion. This image does not move, right? It is your eyes and the blue, yellow, and black, white cones in your eyes that cause it to appear to move as your eyes twitch and move across the surface. These are examples of ambiguous or impossible figures. We talked about figure A already. Figure B is called the devil's pitchfork, and it's very difficult to look at both ends of the pitchfork at the same time because one end looks like it only has 2 tines and the other end appears to have 3. These other two are examples of a Mueller-Lyer illusion. These illusions are essentially illusions of how long 2 objects are. In both C and D, these horizontal structures are the same length, but they appear to be different lengths, first because of these extension lines coming off of them, and then the second one is a result of a misinterpretation of this monocular depth cue where we can see these parallel lines vanishing into the distance. Though A and B are literally the same size, A appears much larger because we perceive it as being much further away. These ambiguous images, these optical illusions, are actually a lot of fun. You can look up a bunch of them online and see how they work. And now that you know about Gestalt, you can sort of see how they function and look at the way you're perceiving these images. Pareidolia is a fairly uniquely human thing because humans look for human faces. Rats look for rat faces too. But humans look for human faces. It's genetically programmed into us to try to find human faces in objects that we're looking at. So this is a few examples. This first one is the image of a face on Mars they thought they'd found. And it disappeared a matter of hours later because really it was just a cluster of rocks and shadows and not a human face. This other one on the top is of course the man on the moon, which I have difficulty seeing the man on the moon actually. I see a rabbit, which is actually fairly common. A lot of ancient cultures believe there was a rabbit rather than a person's face, which leads to many lunar gods and goddesses having rabbits also as their symbols. And then you can see pareidolia in our day-to-day life. This is a bathtub faucet that appears to have eyes, nose, and a mouth. And you can see things that look like human faces all over the place. In fact, your car almost certainly has a human-looking face and an expression. Car designers actually do this on purpose, and they deliberately design their cars to look, for instance, friendly. If they're designing a family vehicle, they're going to make the car look very friendly and happy and safe. If they're designing a midlife crisis car, they may make the car look aggressive and like, I'm gonna go fast and do the thing. Trucks will often look very angry because they're supposed to be super strong and tough. And so you get these illusory facial expressions on cars, and they do it on purpose because of this pareidolia. And it's a marketing technique to make you to make the car look like it's going to do what you want it to do. My Prius actually kind of looks a little bit dim-witted, but that's sort of not its fault. But that's pareidolia for you. We all perceive it as slightly different. There are a number of unusual sensory experiences that humans have and that we've experimented with on a variety of levels. Subliminal perception and subliminal persuasion sort of go very closely together. So with subliminal perception, simply, we perceive and respond to stimuli that are presented below our threshold of awareness. And we know that subliminal perception does exist, particularly, for instance, with subsonics. Several experiments have been done with sounds that are too low pitched for us to actually hear them, but they still vibrate the air. And they cause anger and aggression and general upset when you perceive them. But you can't consciously perceive them. You only process the discomfort without understanding where the discomfort is coming from. Several companies actually designed several experiments for subliminal persuasion. The Coca-Cola company designed probably the most famous of these. The Coca-Cola company paid a great deal of money to have single frames of their product and tagline, Enjoy Coke, placed into several movies. And they did experiments to determine whether or not people purchased more Coke, whether or not people were thirstier when they left the theater, and such things like that. In an attempt to design the subliminal persuasion. And what they found was that they did not sell more Coca-Cola by using this subliminal persuasion. What they found was that people, when they left the theater, were slightly more thirsty than people who were not exposed to the subliminal persuasion, but they were just as likely to purchase water or Sprite or Pepsi as they were to purchase Coca-Cola. Subliminal persuasion does not work, in essence. It does trigger a response in humans, but the response is less than a second long. It's not even long enough for you to tense your muscles to get out of your chair. So for all practical purposes, subliminal persuasion does not work, and there's no way for someone to use single frames of ideas to force you to do things. And it's not possible to do. We've also done several experiments using extrasensory perception. Actually, let me go back for a second and talk about not subliminal persuasion so much, but what these subliminal persuasion experiments led to, which was product placement. They changed dramatically after these subliminal persuasion experiments stopped, and we went into product placement instead. For instance, in the Christopher Reeve's Superman movie, there's a scene where Superman is thrown through a truck of Marlboro cigarettes. The Philip Morris Company paid for most of that movie for that one scene of Superman destroying their truck, because that product placement was enough to promote their product. Coming up into the 90s, the silly movie Twister was paid for by the Pepsi commercial. There is almost no scene in that movie that you don't see the Pepsi logo. It exists in almost every scene, and it's so ubiquitous that you sort of start to ignore it, but it's there, and that actually promotes more product sale than subliminal persuasion did. We have done several experiments using extrasensory perception. The most famous of these was the Gansfield procedure, where they wanted to be able to look at the human's ability to transmit images from one person to another. One of the things that the Gansfield procedure, one example of the Gansfield procedure, was they sent an image of the Union Jack, right? This British flag. Looks like that. And with they would have a sender sitting in a small room, and they would have the sender try and transmit this image. And then the receiver was placed in a very similar room in a different location and attempt to receive the image, and then they would draw whatever that image was. And for instance, the receiver might draw a wagon wheel, like this. Well, it's a remarkable similarity. It's not quite the same, but it's remarkably similar. Now, the Gansfield procedure didn't work often enough for us to say, yes, extrasensory perception and telepathy works. It absolutely does. The Gansfield procedure did not work often enough for us to do that. But it did work often enough for us to go, I wonder. The Gansfield procedure did kind of work. And we've had several similar experiments with extrasensory perception, with precognition, that is the ability to see the future. We've done a bunch of these experiments, and they all sort of end with this, well, it's inconclusive, but it's not a no either. Okay, so that's sort of how we've experienced these experiments with ESP, is that it's definitely not a yes, but it's also not no. The last of these unusual sensory experiences that we're going to talk about is synesthesia. Synesthesia is a mingling of the senses where the association areas of the brain appear to have not differentiated enough. What we think is that newborns are actually born with absolute synesthesia. All of their senses are completely mingled. And during the synaptic pruning that we talked about in Chapter 3, the senses are separated out and become unique, distinct experiences. However, with some people, it's not separated out enough. The most common form of synesthesia is the ability to see sounds, where the individual may get a perception of color or image or shape when they hear a sound. And exactly what it is that they perceive differs from individual to individual. There's also a form of synesthesia when people look at, for instance, numbers, and they perceive that number to be printed in a particular color, no matter what color that number is printed in. I know an individual, for instance, who perceives the color 4 as being purple. And it doesn't matter what color you print the number 4 in. You can do it in red pen or black pen or blue pen. He still perceives it as being purple, no matter what color it actually is, because for him, the number 4 is purple. And there's no reason for it except that that's how his brain is wired. And that is synesthesia, and it's believed that everyone experiences synesthesia at least a little bit, but most people filter it out and ignore it, and it's not something that you're aware of. But for some people, it's an extremely strong awareness of this sensory input.